Again for joining us today. It's a big crowd, and I certainly, or we, I should say, certainly appreciate that. Today's webinar, at first blush might appear to be one that we covered before when we spoke a while back about proper boiler water treatment, but it really isn't, because today we're going to really drill down into the science of deaeration, but without overly confusing the issue with complicated chemical formulations and equally complex mathematical computations. No, today we're going to be looking at deaeration from the perspectives of the why, what, and how of deaerating, giving everyone a better understanding of its place in the boiler room. So as such, here is what we will be covering today. We're going to start with the hydrological cycle, so everyone has a basic understanding of what the impurities we are dealing with are, where they come from, and the damage they can cause if not contained or if they're not eliminated. And then next, we'll move to what deaeration technically is, and then where it is applied. And from here, we'll review the types of deaerators out there and how they operate, while also including their respective advantages and their disadvantages. And then, I thought it would be important and interesting for you to see how a deaerator is built up. Now, not from the manufacturing perspective, but rather the selection and sizing of the essential components which go into a complete deaerator package. And then lastly, we'll review the major benefits of deaeration. And all of this will be included in the final summary before we get into our Q&A that Susan mentioned before, which will also include our expert panel. So, starting with the hydrological cycle, which consists of water precipitating from rain clouds, gets into the lakes and streams, and of course the groundwater, wherein the water percolates through the ground, is used and at some point evaporates back into the cloud formations before just repeating that cycle again. We also know that water is the universal solvent containing dissolved or soluble gases which are highly corrosive when exposed to boilers and boiler system components. But in addition to this, and as indicated on the slide, this water will also come in contact with various minerals in the ground, which, when dissolved, will be found in the boiler's feed water, and they have to be dealt with. For instance, what you see in this chart, for boilers operating between 0 and 300 pounds, are the major impurities which need to be controlled with a sound water treatment program, with the items in red, the oxygen and the carbon dioxide, being the ones which are greatly impacted and mitigated by deaeration. Now, the other impurities are controlled through a good water treatment program using water treatment equipment, and then applying various chemicals in conjunction with proper and consistent monitoring, dosing, and a surface blowdown routine in order to eliminate scale formation, the corrosion, and carryover of boiler water into the system. So as we stated a few months ago when going into detail about a sound water treatment program, deaeration, though a key factor in attaining a highly efficient and long-lasting boiler system, it can't do it alone. We still need chemicals to finish the job, and the amount of the chemicals employed will depend on whether other mechanical devices are in the system, such as water softeners, dealkalizers, maybe an RO, those kinds of things. But suffice to say, at least to some degree, chemicals need to be part of the overall solution. Now, that all said, we'll now spend the remainder of this program concentrating on dealing with these very corrosive gases found in the boiler's feed water: free oxygen and carbon dioxide. Now, here's how it all begins in a boiler which is constructed of steel, as you know, and filled with water. Well, water is the universal solvent, so when water and steel are combined, the chemical reaction starts and begins to dissolve the steel. Now let's add in some dissolved or soluble oxygen contained within the boiler's feed water, and the corrosion continues, but it's at an accelerated rate. And it's not just rusting. Its highly corrosive attack on the boiler's water-side surfaces many times manifesting itself with blisters under which you will find small holes penetrating the tube metal until it fails and then it leaks. And believe me, this doesn't take long to happen. If the free oxygen is not contained or eliminated from the feed water, the boiler can completely fail in a matter of a few months. Now, because remember, we're talking about boilers which are operating under pressure, and as such, elevated temperatures. Here, let me show you what I mean. The chart here shows the accelerating corrosion rate of oxygen when it's exposed to elevated temperatures. Now, as you see in this example, I've highlighted the point using 4 parts per million of oxygen, and I'm also calling your attention to the yellow and red lines representing 86 degrees and 122 degrees, respectively. Now look at the X's. For the yellow one, 86 degrees, follow along to the left of the chart and you will find a corrosion rate of 2 millimeters per year. Increasing the temperature to 122 degrees Fahrenheit, and you find the corrosion rate doubles to 4 parts per million, or 4 millimeters per year. 2 times the rate, with an increase of temperature of just 36 degrees. Okay, that's free oxygen. Well, what about CO2 or carbon dioxide? Well, you know, we know it's not a friend to us except for the trees and the plants out there. And certainly, it's a definite foe for boilers and boiler systems. To put things in perspective with regard to CO2, carbon dioxide, and referring to this slide, you see the chemical reactions taking place in the boiler water and in the system when heat is applied. You see that we start with sodium bicarbonate, apply heat, leaving carbon dioxide and water. Or we have sodium carbonate and water, apply heat, and we have sodium hydroxide and carbon dioxide. In either case, we have CO2 bound in the steam flowing through all the steam piping. And when the steam gives up its latent energy, resulting in condensate or water, it combines with the free CO2 to form carbonic acid, which, as you see there on the screen, H2CO3. And this is what carbonic acid attack looks like. And it is mainly found in the condensate return lines, but can be found in steam lines too. And the other thing to consider with carbonic acid attack is, even though oxygen is 10 times more corrosive than carbon dioxide is 40% more corrosive when working in conjunction with oxygen. So it's imperative that we get rid of as much of these gases from our boiler system as possible to not only save energy by reducing blowdown, but preserve the life of these very expensive and important assets as well. Okay, so how is it accomplished? Very simply, applying heat in the proper way. Remember I showed you a slide before which indicated the role heat plays in changing chemical formulations, resulting in free carbon dioxide combining with water to form carbonic acid? It all started with carbonates of alkalinity in the feed water. Well, this CO2 can be totally removed from the system by applying heat in conjunction with another factor, which I'll discuss in just a minute. And then we also have the oxygen in the feed water, which comes in through atmospheric absorption from pump seals, from leaks in piping on the suction side of pumps, from vacuums in the system, and so on. This, too, is effectively removed by properly applying the heat. For instance, and looking at the scientific basics, oxygen loses its solubility in water when it is heated. Note in the slide on the screen now, we have temperature across the bottom horizontal and parts per million of oxygen on the vertical to your left. Note how at 50 degrees, which is close to raw makeup water temperature in many places, we have almost 8 parts per million of oxygen. Then as we increase the temperature to 210 degrees, we drop to almost 0. The oxygen is almost entirely driven off. And it's the same with CO2, but there's another factor, as I mentioned before with CO2, that you need to be aware of. Again, the basic science of water chemistry. Carbon dioxide will form in the boiler's feed tank as the water is heated. And as shown in the slide before, the amount of CO2 formation is dependent upon the amount of carbonates in the feed water, especially bicarbonate. The other factor with CO2 and carbonic acid attack is maintaining the proper pH level in the feed water tank and the boiler. As you can see on the slide, the pH needs to be above 8.5 to inhibit corrosion. And many chemical experts recommend the pH between 9 and 12.5, with boilers operating between 0 and 300 pounds, which is what we're talking about today. And I've seen where a pH of 11 seems to be the most common target. All right, so much for the why of deaerator science. Now let's spend the balance of our time looking at the what and how factors. Firstly, we need to understand and appreciate the complexity of water, not only its constituents, but its characteristics. For instance, water possesses a high degree of surface tension, which tenaciously holds things in place unless a surfactant is applied or some other means are imposed on the water to reduce the tension, and that's exactly what deaeration does. It begins by reducing the surface tension through spraying or filming of the feed water. And then it heats, it agitates, and then liberates the corrosive gases back to the atmosphere, thereby avoiding their corrosive effects on the carbon steel that they come in contact with, be it the boiler or the connected piping system. So in essence, we start with the deaerator having a system which either sprays or films, spreads out the water to reduce the surface tension for eventual gas bubble release. And then we heat that water, which causes the gases to lose their solubility and form the bubbles. This is followed by a mechanical agitation or a scrubbing process, which then liberates the gases, allowing them to flow to the atmosphere. Now, the other thing we need to keep in mind about deaerators is their ability to hold hot condensate returning from the system in addition to the cold makeup water. This is very important when trying to conserve the fuel spend. Here, let me show you why. To begin with, understand these deaerators operate under pressure with designs most commonly rated at 50 pounds. That's the design pressure of the tank, and operating between 5 pounds and 10 pounds. 5 pounds is 227 degrees, 10 pounds is 240 degrees saturated. Now, there are designs available for higher design and operating pressures, but for our discussion today, we'll limit our focus on 50-pound designs and operating between 5 and 10 pounds. So then, referring to the chart on the screen now, notice the amount of sensible energy required to convert a pound of water to a pound of steam at 5 or 10 pounds of pressure. And this is a typical steam table based on a 32-degree incoming water. Point is, if I can raise that feed water temperature coming into the deaerator by returning more hot condensate, I can reduce the sensible BTU requirement from my boiler's burner to make the required amount of steam to reach the saturation by a ratio of 1:1. And remember, for every 10 degree of improvement, I gain 1% in efficiency. I raise my feed water by 10 degrees, I gain 1%. Here, let me show you more specifically what I mean. Let's assume we have an 800 horsepower boiler serving a process load, and we're wasting all the condensate. An 800 horsepower boiler evaporates 27,600 pounds of steam per hour. And at 8.3 pounds per gallon, that's 3,325 gallons of water per hour. Now let's say our incoming water is at 50 degrees. I'm operating my DA at 5 pounds, and that's 227 degrees Fahrenheit. This means I have to raise the temperature of each pound of water to reach saturation temperature before I can add the heat for a phase change into steam, that latent heat. That sensible energy, that's 177 BTUs per pound times the 27,600 pounds equals 4.9 million BTUs I have to add. And if I'm burning natural gas at 50 cents per therm, and a therm is 100,000 BTUs, that's costing me 49 therms times 50 cents equals 25 bucks an hour. And if I operate 4,000 hours per year, that's $100,000 a year in cost for just heating the feed water to get to the point where I can add the required BTUs of latent energy to convert that pound of water to steam. Now, on the other hand, let's say we returned a portion of the condensate, giving us a blend of feed water temperature equaling 125 degrees Fahrenheit. Now all we have to do is add 102 BTUs per pound of water, which equates to 28 therms times 50 cents is $14 an hour times 4,000 hours, $56,000 a year, or a savings of $44,000 a year because we returned that condensate. So it always pays to return as much clean condensate as possible to maximize efficiency, regardless if we're using a deaerator or a vented receiver. Now, before getting into the various deaerator designs in operation, we are often asked, when should I even consider a deaerator? Or said another way, what are the applications? Well, as you can see on the slide, border plants that are operating at 75 pounds or higher are candidates, okay? Your deaerator is not going to pay for itself for low pressure steam. So 75 pounds or higher. Plants with no standby capacity. Okay, so if you don't have another boiler, we want to make sure the one we have is operating and reliable. So a deaerator is certainly going to help along those lines. And plants with critical loads. I mean, it just goes without saying. If you've got a critical load where you could lose your batch, and there's critical temperatures and pressures that have to be maintained, a deaerator should be seriously considered. And then all plants operating with 25% makeup or more. Now for the various types of deaerators and how they operate, we'll begin with the spray type. As you can see on the screen, these deaerators normally range in capacities from about 7,000 pounds of steam per hour to 280,000 pounds. This rating, of course, is what the boilers or boilers produce, and the deaerator needs to pick up this evaporation rate in the form of boiler feed water. Now, looking at the cross-section on the screen, you can see where the design gets its name based on the spray cone assembly located in the tank itself, which is where the deaeration is taking place with this particular type. You also see these are complete packages, including the feed water tank, the stand, the pumps, and all the controls needed to properly function. Now, for a closer look at the business end of the spray deaerator, we see a cross-section of the actual spray cone assembly, which is the device which reduces the surface tension of the water by spraying the influent as it comes in contact with the steam entering at the same point. It is in this cone section where the water is raised in temperature to within, let's say, 2 to 3 degrees of saturation, and in so doing, driving off much of the oxygen and the CO2 through the vent. As this steam condenses and combines with this hot feed water influent, it collects in the cone and is pushed through the spring-loaded spray nozzle, which is also seeing live steam. And here it's agitated and misting, and the mix will be heated to the saturation temperature, and if we're talking 5 pounds, that's 227 degrees, thereby finishing the deaeration of the liquid before it collects into the integral feed tank. So then the remaining steam after the final stage is condensed, leaving only the remaining O2 and CO2 to exit the vent. The next type of deaerator that we want to consider is the packed column, with a typical capacity of 1,500 to 135,000 pounds per hour, and unlike the spray type, has 2 separate vessels, one for deaerating, which is the column, and one for holding the deaerated feed water, the storage tank below. And similar to the spray, It also is equipped as a complete package with the stand, the pumps, and the controls. Now, taking a closer look, it's plainly obvious how it got its name with the deaerating column positioned on top of the tank and packed with rings, normally of stainless steel, and they're providing the medium for lessening the surface tension of the water while also providing an excellent means of commingling the water with the steam for outstanding counterflow heat transfer and heating, after which the corrosive gases, the O2 and the CO2, release to atmosphere. Now, operationally, you see in the cross-section of the column the makeup water and or condensate entering at the top and the steam entering at the bottom through the top of the tank and into the bottom of the column. At the top of the column, you also find the spray assembly and the vent condensing chamber. It is in this general area where much of the feed water is deaerated, coming within a couple of degrees, as I mentioned, of saturation. The feed water then continues to drop downward, cascading over those rings, staying in close contact with the steam as it heats the water to saturation temperature in a counterflow direction. Then, releasing the non-condensable gases, the O2 and the CO2, to atmosphere through the top vent, which is indicated on the picture. Now, the last type of DA that we're going to be reviewing today is the tray-type deaerator. And as you can see, they can get quite large, not only in capacity, but physical size as well. And you're going to be finding a lot of this type of deaerator associated with and supporting large industrial water tube boilers. Now, the tray deaerator works very much like the column type. However, rather than rings being used to reduce the water surface tension while providing an effective heat transfer medium, stainless steel trays are used. And similar to the other designs, the tray deaerator includes the spray nozzle for injecting the untreated water into the unit, the steam injection point, the vent condenser, the downcomer or the path for the deaerated water to flow into the feed tank, and a tapping for high temperature returns to be introduced into the deaerating tank to assist in the deaerating process, saving energy as we previously noted. Okay, those are the three types of deaerators. Now, what is the advantage and disadvantage for each? Well, looking at the slide now on the screen, I'm showing you that, but it requires a bit of explanation. And to do this, let's focus our attention on the red highlights under the advantages with the spray and the column types, as they can become disadvantages depending on the type we are comparing. For instance, the spray deaerator, when comparing similar capacities, will be less costly and will weigh less. It also requires far less headroom, which is a key advantage in many boiler rooms, and its capacity range is wide, spanning 7,000 to 280,000 pounds per hour. So these are all great advantages. However, as you can also see, its disadvantages are actually pluses for the two other types, and especially impacting reliability. And this is because the spray deaerator has a couple of moving parts, which may require more mechanical maintenance in the field over the life of the equipment, thereby affecting routine operating cost and reliability. Now, more specifically, the spray deaerator utilizes two stages of deaeration. In the spray head area, about 90% of the aeration is accomplished, and then the other 10% is done in the scrubbing or spring-loaded nozzle area. And because of these moving parts and associated dynamics, misalignments can occur, affecting the reliable and consistent deaerating process. However, I might quickly add, most of these adjustments, if required, are performed during the normal annual inspection and cleaning of the boiler and the associated support equipment. So possible downtime for DA maintenance with the spray is certainly mitigated in this instance. And then there's the question of high pressure returns. With the spray deaerator, we're limited to a large extent due to its intolerance to handle, certain amounts of flash steam. Not the same problem in the column and tray, as they have counterflow design taking place in separate tanks, wherein flash steam is occurring in the feed tank and does not impede the deaerating process as it might with the spray type. So, in the final analysis, and when everything is said and done, all of these deaerators eliminate oxygen to 0.005 cc's per liter, which is about 7 parts per billion, a real dry martini. It's just a matter of choosing the one which best meets your headroom and floor loading needs, your capacity and system requirements, and of course your budget. Now, before moving on to the selection of the major components for the deaerator, I think I would be remiss if I didn't come back to capturing all the condensate we possibly can, as this is truly liquid gold. On the screen now, I've returned to the steam table just to re-emphasize again how much sensible energy goes into each pound of water as we increase pressure before arriving at saturation temperature. And at this point, you may be asking, Steve, well, why are you showing me steam tables highlighting 80 and 100 pounds when I've been talking about deaerators operating between 5 and 10? Well, as mentioned before, there are high-pressure DAs available, and they would be able to handle pressures like this, but that's not why I'm showing you the table. The reason is to draw your attention to this piece of equipment, the high-pressure receiver tank. You know, maybe we have or can only fit a spray-type deaerator into our boiler room, and we have a system which could provide considerable high-pressure returns, which we are currently flashing off as we reduce pressure. In this situation, we could return this condensate to a separate high-pressure receiver as shown, knowing this condensate has not seen atmosphere and is fully deaerated. We then only need to deaerate the makeup water through the spray deaerator, feed this influent into our high-pressure receiver, and feed the boiler from the high-pressure receiver. Remember, for each 10-degree rise in feed water temperature, I'm going to say it again, we gain 1% in efficiency. And that says nothing about the water cost, the sewer charges, and the chemical charges that this venting incurs and that could be saved. All right, enough of that. Let's move on to how the major components are selected, and we'll use a spray-type DA for our example, as this is a very popular design found in many boiler rooms. Starting with the spray cone and tank assembly, we begin with the capacity of the boiler load, and for this, let's say we have a 200 horsepower boiler generating 6,900 pounds of steam per hour, or said another way, it evaporates 831 gallons of water an hour. This then is the maximum capacity for the spray cone. As far as the tank is concerned, this is normally sized based on the minutes of storage the system requires. Let's say for our purposes today it's 10 minutes. At an evaporation rate of 831 gallons per hour for this 200 horsepower boiler, this is a 140 gallon tank, but let's call it 150 gallons just to be safe. The next thing that we want to select is the makeup valve for feeding the raw makeup water into the spray cone assembly. Now, as noted on the screen now, this valve can either be mechanical as shown, or it can be pneumatically actuated or electronically. So we've got several options here. Now, to size the valve, we use the formula shown on the screen in the lower right side and corner. Take the square root of the result from the inlet water pressure minus the tank pressure and minus the nozzle pressure times the CV value. And the CV value is the valve's coefficient capacity, meaning at 60 degrees F water temperature, what is the amount I can pass across that valve to get a 1 pound drop? Now, as you can see in the example, the answer for 50 pound incoming water with associated pressure drops and the square root function applied to this particular result times the CV value of 12 gives us 73.2 GPM that this makeup valve has to accommodate. Next, we are going to have to select the pressure reducing valve, or the PRV. This starts by determining the maximum pumping rate out of the DA at full load. In other words, the total flow, which comes from pounds per hour of the heating steam, the condensate that may be returning, and the makeup water. And from here, we need to determine the average mix temperature of the feed water to be deaerated, including the raw makeup temperature and the returning condensate temperature, along with their percentages. So, given this information, the amount of steam required to heat this water is determined, and leading to the appropriate size selection for the valve based on the boiler's operating pressure. And this information is very, very adequately provided by manufacturers such as Spence and Fisher. And by the way, these manufacturers have selection charts available for determining what I just briefly went through, given the respective specifics, including the total flow required, the temperatures, and the pressures. Well, now it's time to select the pump, or the pumps for the job. Now, for a single boiler operation, what we normally see are one operating pump and then one matched pump as a standby. As you see on the screen now, I'm showing centrifugal pumps, which are the most commonly applied and normally come in three basic variations, including the vertical multi-stage, the flex coupled, and the close couple models. To begin with, selecting a pump for the deaerator application, and assuming we are operating at 5 pounds in the deaerator, we start with the boiler horsepower and the evaporation rate, which results in the GPM flow required. Then to this result, we need to add a safety factor. And this will vary depending on whether the pump is continuously running or is of the intermittent operation type. Now, if it's continuous, we normally add 15% to account for the pump wear and blowdown losses, and then we add the pump manufacturer's recommended minimum flow requirement, in other words, the recirc requirement. On the other hand, we normally add 50% for the intermittent pump, as we want to make sure that we have enough water to avoid a low water occurrence when the pump starts and things begin to flow. And next, we have to concern ourselves with the pressure the pump has to overcome in order to get the water into the boiler. It's referred to as TDH, or total dynamic head. Now, to determine this, we need to allow for the specific gravity changes for the hot water, and also calculate the pressure and line losses, converting that to feet of head, and it's 2.31 feet per pound, in order to read the pump curve, which I'll show you in a minute. Now, at the same time, we need to determine the NPSHR, which is the net positive suction head required for the pump to keep it from cavitating at the duty points that we've selected. Now, here's an example of what I'm referring to. And for illustrative purposes, I'm showing you a centrifugal pump with a very high pumping rate, but the curves show up better, and it's all relative anyway. So following the red arrows, you see where a flow rate of 600 GPM, and we have calculated a TDH of 50 feet. Now, looking at the intersecting curves, we see the 1750 RPM pump will require an 8.5-inch impeller in the pump. It will operate at about 82% efficiency at those duty points with a 10 horsepower motor requirement. And also the NPSHR, or the net positive suction head required at those duty points for this manufacturer's pump, is shown on the bottom right of the graph and will be about 8.5 feet. So, understanding what is shown on a pump selection curve, here is how we arrive at the duty points to apply to the curve for selecting our particular pump for the 200 horsepower boiler operating at 100 pounds and using a continuously running centrifugal pump. So you see up on top here, we have a 200 horsepower boiler. We use a factor here which will get us to GPM flow, or 13.8 gallons per minute. And if we've got a continuous operation, we add the 15%, so now we're up to 16 gallons per minute. If it's intermittent, we'd add 50, we'd be at 21. So the boiler operating pressure, as far as calculating the total dynamic head, we take the boiler operating pressure plus the feed water valve loss plus the line loss equals total pressure times 2.31 to get us into feet, and then we divide that by the specific gravity of the water at that temperature. And this would be about 227 degrees. At 60 degrees, it would be 1. At 227, it's 0.95. So you see the math down below. The formula is now calculated. 100 pounds plus 25 plus 5. So the 100 pounds is the boiler operating pressure. 25 is my loss across the valve. 5 pounds for line losses, which also includes a pound or two to overcome the pressure in the boiler, equals 135 pounds times 2.31 is 301 feet, and then I divide that by my specific gravity of water at that temperature, and I mentioned 227 degrees. I've got a total dynamic head of 317 feet. Then I would look on that same pump curve to determine at those duty points what is the NPSHR required. You know, before leaving pumps, I did want to draw your attention to a couple things which have caused people problems over the years. Problems, you know, which could have been avoided if they were aware of what could happen. For instance, in this pump curve, look at the blue and black arrows and the respective TDH duty points, total dynamic head duty points. For the black arrow, it's 280 feet, and for the blue, it's 180 feet. Now let's assume the pump was selected for the 280-foot duty point, but sometime down the road, that duty point changed, dropping to 180 feet. We could have decided to lower the operating pressure of the boiler because we wanted to save energy, and that will save energy. But notice on the curve where our NPSHR went from 5 feet at 280 feet TDH to 6 feet at the reduced pressure of 180 feet. This could cause cavitation and pump failure. Now here's another example. In this case, we'll assume the boiler was changed out because of an increase in load, thereby increasing the boiler capacity. But the DA stayed the same, except the pumps were changed out to add more capacity, but no other changes were made to account for the possible cavitation of these pumps, such as increasing the stand height. As you can see, we went from 60 gallons per minute, the blue arrow, to 100 gallons per minute, which is the red arrow, with the same TDH requirement of 200 feet. Look what happened to my NPSH requirement on the pump. At 60 GPM, I was at about 3 feet, but at the greater flow rate of 100 GPM, I doubled to 6 feet. Think this doesn't happen? Believe me, it does. Also note that changing the operating parameters and conditions of the boiler and associated equipment can also affect the size of the PRV valve, your makeup valve, and safety valves. So being attuned to possible impacts before making any radical changes can certainly save a lot of costs and certainly a lot of headaches in the future. Getting back now to our 200 horsepower boiler example and the information we have deciphered about our respective requirements, we can now select the stand for the DA, and which also serves as the platform for my pumps, as you can see. We said before that our boiler will evaporate 831 gallons of water per hour, and we want 10 minutes of storage, or let's say we want to hold at least 150 gallons. And with this information, the tank is selected. We also know what our pumping requirements are with a flow rate of, say, 16 gallons per minute and a TDH of 328 feet. So taking this information, we go to the pump curve, example I just showed you before, and find we have an NPSHR requirement of, say, 5 feet, meaning the stand must be constructed to give me a minimum of 5 feet above my pump's inlet center line, measuring from the normal water line in the tank down to the center line of the pump's inlet, and this is to prevent the cavitation. So to be safe, though, we normally add about 2 feet above, making it 7 feet above the pump's inlet in this case. And by the way, that's what we refer to as NPSHA, alpha, net positive suction head available versus what the pump manufacturer is requiring, NPSHR. Now, the last important device we need to consider is the safety valve or valves for the deaerator. Remember, these are pressure vessels built per ASME Code Section 8, Division 1, unfired pressure vessels, and as such, require a safety valve or valves which are normally set at the maximum allowable working pressure of the vessel. And in most cases, I mentioned before, this is 50 pounds. Of course, they are there to protect the vessel from overpressurizing should the PRV fail open and or excessive amounts of high pressure condensate enter the tank, causing its pressure to elevate. For sizing purposes, these valves need to have enough relieving capacity, which includes the area and the diameter, to account for failure of the PRV failing open and the pressure controls on the boiler failing. In other words, if that were to happen, and we had a boiler operating at 125 pounds, and our PRV was sized for that pressure, but the safeties on the boiler were set at 150 pounds, we would have to reference the same size PRV, the one that we selected, but now at the 150-pound pressure to see how much steam the safety valve would need to relieve in pounds of steam per hour. It's all about additional safety because even though the deaerator is not fired, it's a boiler. They are still containing liquid under pressure with very high temperatures, 5 pounds, 227 degrees, 10 pounds, 240 degrees, scalding. And if the vessel ruptures, it can cause very serious damage to property, life, and limb. And the safety valve is our last hope if this happens. Very important device. So, DA benefits. Hotter boiler feed water saves fuel energy. 10 degrees F, gain 1%. Return the condensate. Saves on chemical costs. We're not using as much sulfite. This then reduces blowdown, saves water, chemicals, and sewer charges. Better protects the boiler and piping system, reduces downtime and capital expense, and reduces thermal shock, especially in the feed water tapping area of the boiler. Major takeaways for today, I would say, you got to remember that DA removes oxygen and carbon dioxide. Oxygen corrosion increases with temperature. Remember that slide I showed you early on. Carbon dioxide is 40% more corrosive with oxygen present. The deaerator gets rid of that. DAs reduce water surface tension. They heat, they agitate, and they liberate. That's what these machines do. 3 types, the spray, the tray, and the column. Return condensate as hot as possible. Look at those possible options that I gave you. Remember the column and the spray deaerator, the column and the tray deaerator will accept high pressure condensate return. Also think about the high pressure receiver. The spray is limited in the amount of high temperature condensate that it can handle. That's one of the downsides of it. And changing duty points on a pump can cause cavitation. Safety valves are the last line of defense. How about some questions?